Greetings. I wanted to talk today about debug for I3C. We're going to take a deeper dive into some topics. For those of you who saw the previous webcast on debug for I3C, this will go into some deeper details. For those of you who didn't see the previous webcast, we're going to give a little bit of an introduction to debug for I3C and what it's about, and hopefully cover a good enough detail to provide a level of interest. Thanks for joining today. Today we're going to talk about a brief overview of debug for I3C. We're going to talk about the network adapters, the various sources and sinks of information that a debug for I3C device can make available. We'll talk about the command codes, the CCCs that are defined in the debug for I3C specification. We'll talk about session management and the various types of debug resets that can be applied to debug logic. We'll talk about the in-band interrupts for I3C for the various types of events that can happen. We'll talk about debug ecosystem a little bit, about what it takes to enable MIPI debug for I3C, and then we'll come to some conclusions about what we can do and how we can go from there. So for those of you who aren't as aware, MIPI debug for I3C is a new debug interface standard that MIPI is defining and creating, and this really is meant to address existing interface solution gaps in places where things like JTAG and I2C and UART really aren't addressing parts of the debug ecosystem. So we're looking to enable debug of multiple different components on the board. This is not just intended to be a point-to-point, DTS to target system. We're enabling a place where we can go in and have multiple different chips, SoCs, devices be able to be controlled by the DTS for debug. We want a connection place from multiple different places, like, for example, a Type-C receptacle or different pin interfaces or different connection points. And you see in the diagram here that the application processor itself could even be a DTS in some use cases, or a modem itself could even be a DTS and could come in over a given network interface. Or, we've got the classic debug connection through a dedicated port, through a direct connector. So I3C provides us the ability to go do these things in ways that the existing interface solutions don't allow right now. Because I3C also has features that allow for devices to come up at different times through hot join, we have the ability now to do things that allow the application to basically come out of low power states and come up on the bus as they need to. So we think this gives us a lot more robust and a lot more scalable and power management aware way to connect to debug, whereas existing classic interfaces don't have that right now. So again, we're building on the core capabilities of I3C, and that includes classic I3C, the full specification, or MIPI I3C Basic, which offers kind of a reduced feature set, essential capabilities of I3C. This could be a dedicated bus, for example, MIPI I3C used as just point-to-point connection for debug devices, or a debug-only bus for multiple devices, or it could be shared between other uses of I3C on the same bus as well. That's also a possibility. Because we've defined the byte-oriented streaming interface here, we can have different protocols, and each of those have network adapters that we've defined as kind of different protocol layers here. So it allows each of the target systems to expose different interfaces and points as a network adapter from one physical connection or multiple entry points, as we saw earlier. We allow the debug and test system, the DTS, to send broadcast actions like halts or resets, or we allow them to send directed actions to individual targets on the bus. And because I3C has in-band interrupts, we can send event notifications through in-band interrupts like a trigger or a request back to the DTS. That can say, hey, something important happened, you need to go deal with it. Looking at the conceptual system diagram here, again, this will be familiar for those who attended the previous webcast. We have a kind of a layered system architecture that shows how the various pieces of the stack talk to each other. The diagram on the left shows things in a diagram that looks like different stack layers here. At the very bottom, we see the I3C link layer. This kind of shows the physical bus. The layer up from that shows the transport and the network, which just kind of shows how bytes are streamed across there. The next level up in pink shows the different network adapters, and this kind of shows the conceptual model of how the different types of streaming byte layers are arranged and oriented for the different protocols. And then on the application side, we see different drivers or different possible software stacks that can take advantage of these things and assign meaning to them and provide layers to applications. On the right side here, we have the infrastructure and the sources that connect to the different parts of debug functions and logic. And then in the functional diagram on the right, we see a little more detail, which shows various FIFOs. We show the status and the state machine for the session management in here that connects to the I3C transport layer and then the debug function above it. So this just kind of represents how we envision a possible debug device being architected and structured here with the different inbound and outbound FIFOs. Now, again, the inbound and the outbound FIFOs are going to depend very much on the type of debug network adapter that's being used. And we'll get into more detail on that in a little bit. So again, the network adapters are seen as kind of common logic, and they're going to depend on how the different protocols are defined. A target system could have several different network adapters. You could have, for example, a sneak peek network adapter that's used for command and control. You could have a trace network adapter for TWP or STP used for trace streaming or system trace streaming. The debug functions themselves could be sources or sinks, or in Sneak Peek's case, both a source and a sink for receiving commands and responses. And that's shown by the green box on the top here. And for Sneak Peek's case, we show a connection to a TAP network or debug registers. For other protocols like SAM, we see, register access or memory access or other infrastructure here. And we see all these things being connected through debug extensions and controlled by the various CCCs that Debug for I3C defines and makes available to kind of control this whole operation, manage the state machine, manage the FIFOs, manage the sessions, all that. And this really is what's defined by Debug for I3C as a common framework for managing and taking care of all these things. So network adapter, we've kind of touched on this a little bit. The network adapter is basically conceived as a mechanism for communicating with debug functions within a target system. It could be an inbound data pipe, an outbound data pipe, or both. And we see these being accessed and mapped to I3C private writes and private reads. And you could have these mapped to a single instance of a debug function, and each one of them has a particular protocol. In Debug for I3C, we have these defined so that there's a maximum of 16 of these and a minimum of 1. And how many and which one of these you have really depends on the design of the debug device that's being designed by implementers. And network adapters could use all different protocols or the same protocols. And we'll touch on what those are right here. Again, these are defined in more detail in the specification, but we'll touch on them briefly here. Sneak Peek is the one that's been defined by MIPI for debug communications. That's used for bidirectional transfer of blocks, and this really is kind of a command response engine here. Trace Wrapper Protocol, or TWP, is used for streaming trace data output, and this is kind of oriented more for hardware trace engines. System Trace Protocol is a one-directional protocol used for streaming of trace bytes. And we call this System Trace Macro Cells here for software trace engines, typically. Simplified Address Map Protocol, or SAM for short. This is a more simple address mapped access, and typically we see this used more for register access or memory. UART, again, this is a classic mapping of things we see for UARTs, and it's really just a character-oriented software agents used for things like scanf or printf. Again, bidirectional. And there's also space for implementation defined for those who look at these things and say, our use case doesn't map exactly to any one of these things. We want something that has our own custom byte protocol in this. There's space to go do something different. So again, showing all these as a possibility for a device that has pretty much one of everything here. They're all identified by a different index. Then this is an example of one that has a little bit of everything. It's got a Sneak Peek engine. It's got an STM for system software. It's got a SAM engine for registers and memory. It's got a TWP formatter for hardware trace sources. It's got a UART for scanf and printf. And it's got all these things being managed by a single network and transport layer on the target side. Now, any individual Debug for I3C device doesn't exactly have to look like this or have one of everything or use all the possible indexes. The choice of these is up to the implementer. For SPP, again, a brief overview of these things. This is a fairly rich mechanism. SPP implements these things as private writes and private reads. And for example, writing a Sneak Peek transfer block is basically one or more commands at a time. And reading them back is basically reading back the responses. And this works by address map mechanism here. And typically we've seen these used to replace things like JTAG access to things like TAP networks on the inside of silicon implementations. And I think for more information, you can go look at MIPI's sneak peek specification. But the thing to know about this is that it's basically formatted as what we call tiny SPP, which is new for MIPI Sneak Peek 2.0. And it basically sets this up so that you can do reads and writes to the address map mechanism defined by Sneak Peek to go read or write commands and then read responses back from the address mapping that's defined by Sneak Peek. So for example, if you wanted to write a command packet that has 3 different commands in a single packet here, you'd structure this as a private write. And we see this mapped as kind of an I3C packet below here, writing to the dynamic address of the particular target in question, getting acknowledgement, and then the stream of bytes. And that stream of bytes is broken up as 3 different command packets in one Sneak Peek transfer block. And again, the framing for the response is structured very similarly. You do a read of that same target's dynamic address, get an acknowledgement, and then see the Sneak Peek transfer block with all 3 of the different response blocks there. TWP, again, we've touched on this earlier. This is used for trace data output. And we kind of have an assumption there's a TWP formatting engine inside that's kind of putting these in here. You can have one or multiple different trace sources involved in formatting these things here. And since this is really one directional, this is outbound from the perspective of the debug device here, it's really accessed only by private reads. And you can see more reference on what TWP means here in the MIPI TWP specification for trace wrapper protocol. Mapping this in here for TWP frames, you can see these things proceed in order. And you can imagine these stacking up in a FIFO or a buffer. And then as we read these things, one chunk or one packet at a time here, we see the individual TWP frames being spread out across and then filled up within the maximum size of the read. So these 5 different TWP frames are kind of spread out and basically parceled out as we need to. STP works very similarly. This is used for trace data output, and again, typically oriented for software tracing. So we see these things spread out across one or more different private read transfers. Again, the exact semantics and meanings of STP is in the MIPI system trace protocol specification, but it's framed very similarly. You can see a FIFO or a queue of STP packets here. You can see these spread out across multiple I3C private read transactions here. Starting off by reading the dynamic address, getting the first few and then a piece of the next one, and then spreading out to the next, and then finally finishing on the 3rd read. SAM adapter here for simplified address mapped protocol is a bidirectional protocol. We see this being used for read and write transactions, typically for simpler register access, simpler memory or memory bursts. These are kind of structured very similarly to classic I3C write then read semantics, or even just I3C writes for simple sets or writes. By write then read, what we mean is you typically have to write something like a command byte and then an offset, and then after that turn around and do a read to see the results of that. And the semantics of that are set up so that you kind of have to do, you write the offset in the command and then go back and read the product and read the result of that. And the SAM engine's behavior is specified entirely within debug for I3C specification. So for example, we see set or write as a command by itself. We see, addressing the dynamic address here, command byte parameters and optional data bytes. This would be a set or a write command here. There's various types of set or write commands, and the details are all in the debug for I3C specification here. And then for get or read, we see the write then read semantics. You see the first half, which is writing the command byte and the parameter bytes. And the second half is after the turnaround, doing a read and then fetching the data as the result of that command and the parameters that are associated with it. For the common command codes, we see these as ways to control the debug logic here. And there's a couple different things that we have here. We have debug opcode, which really is controlling the operation of given network adapters or reading the parameters of the device or getting its configuration for initialization time. Some of these are write-only versions with opcodes. Some of these opcodes are write then read, similar to what you saw with the SAM adapter. Do a write followed by a read, very same semantics there applied to CCCs. Debug actions, we see these being write-only. They're, again, directed to a specific target or broadcast to all debug-capable targets on the bus. So stepping into debug opcodes, we see some very specific uses here. We see, read-only capabilities. Again, this is followed by write. This is a write then read only version. Then all the ones that are read here are, of course, write then read. That's how they work. We have the config opcode, which really does configuration of how to get data from the device. So is it polling based or is it based on interrupts with IBIs? We see the network adapter controls here, how to start or stop or manage the various session management state machines here. We'll touch on those in a bit. We see the FIFO threshold and the FIFO action controls. These deal with the FIFO levels and what to do in various actions and states within the network adapter logic. Select here is an interesting one. It's basically write only. And in a system with multiple network adapters, this is the one that actually is interesting because it selects which of those network adapters is active and being used at that time. So when you select a particular network adapter using the select opcode, that basically says, okay, after I've selected that network adapter, private writes from the DTS go here, and private reads initiated by the DTS pull from there. You can think of it like a virtual MUX in a way, and say, I'm now addressing and pulling and pushing data to and from this pair of FIFOs. So if you have a device that's got a sneak peek adapter here and a trace adapter here, if it's TWP or SWP, excuse me, and you select the sneak peek one, at that point, the private writes and the private reads in the device are, hooked up to the sneak peek FIFOs, and they become, writes become a command block and reads become a response block. When you do the select CCC with the opcode here to select the trace adapter, the private writes really don't have a meaning. The private reads just pull data from that trace adapter. And that's why we think of it like a virtual MUX. Report error is basically a way for a DTS to inform the network adapter logic that, hey, something happened, or we got some data we weren't expecting, or something looked wrong. We're telling you something went very, very wrong, and so update your state machines accordingly. And I believe that has the ability to go propagate back into the network adapter logic and have it be handled within there. Debug actions, again, these are built on ways for the DTS to inform each of the targets that I want you individually or collectively to all perform something at the same time. Really what we see is a framework for implementer-defined actions to be defined here. And these could be halts. These could be things like breakpoints. These could be things like vendor-defined triggers. These could be things like other coordinated actions across a board. But the goal of these things is to say we have a method for, and again, debug reset, which is a key one, which just clears things out and gets them back to a fresh state. But the goal is to say I want to build up a set of these things. And by doing them with a start set and then a bunch of other things and then exec set, you have the ability to frame them and say start first, collect a bunch of other things in the middle, and then exec. And then all the devices that are listening and see debug action with a start set and the debug action with an exec set will do all those things in the middle as long as they all understand what those things mean. So we really are looking for implementers to think creatively about the implementer-defined actions inside here and see, what interesting and useful debug actions can we do in this implementer-defined space, and then have start and exec set be the way to go, have the DTS inform one device or multiple devices do these things at the same time. So it's a pretty powerful mechanism. So session management, let's touch on this for a bit. Each of the network adapters has its own internal state machine, and there are basically states like started, starting, stopped, stopping. I don't want to show the exact diagram here because the meaning of these things really depends on the type of network adapter, and I think people who are interested in that can go very much look at the specification and find out what that means. But the goal of this is to basically give people the control to manage the state machine and the transitions between the various states and say it's time to transition from starting to started or transition from stopping to stopped. And that gives control over the network adapter and the debug function behind it to say, I want to, get to a running state or get to a stopped state and basically, shut down sessions or set up new sessions or deal with other required actions that are needed for that. Debug for I3C defines a state machine that's kind of expected to happen within the target system. And there's also a similar conceptual model for a state machine that happens within the DTS itself that could be very well be applied to software layers inside the system that's running it. And those two things are very, very closely correlated. And again, it really depends on the network adapter types. For example, sessions for trace protocols probably need to be thought of and conceived very differently than sessions for Sneak Peek, where it's command response. So again, but you have powerful control over what the states are and how these things are managed with the debug opcode CCC here. And again, this is common logic. These are things that are, the framework for how to communicate these things is commonly defined within debug for I3C. Resets. So there's a couple different ways to reset. So one of the things that we defined here is the debug action CCC with the debug reset value. A couple slides ago, we touched on a way to send this opcode with the debug action CCC that just says, go reset your debug logic. And that will basically take care of everything past a certain point and perhaps even debug functions beyond that. Also, for those who have I3C with target reset pattern available, and that's I3C 1.1 or above, you have the CCC called reset action with the target reset pattern, and you can use I3C CCCs with defining bytes to go say, I want to build up some collected reset actions that can say, when I collect these actions together and send the target reset pattern, I want you to go reset these things. So, and we kind of fit these together in kind of a combined reset and layer model here for I3C with, the peripheral logic, which is the link and the transport layer, the debug reset, which is either one of these two things I just mentioned earlier, either the debug action or the target reset logic, or, you have the whole target or whole chip type reset here, which basically allows the DTS to control reset of the entire device. So you have some pretty fine-grained control of how to reset a device using I3C for those who have access to I3C 1.1 or later. For in-band interrupts, there's a way to for the target system to let the DTS know that certain conditions or status or errors have happened. The first of these, of course, is debug status. This indicates that, for example, a FIFO threshold has been met or a session is stopped. I mean, this could be something that was happened as requested. For example, you send a state machine command to stop a session. It comes back and says, okay, I stopped. Or, a more advanced condition like a processor in the debug logic halted. For debug error, there's various types of error conditions that can be used for notifications. It could be an I3C transport layer, any one of the various, target type errors in I3C itself, or some error within the network adapter logic or further on within the debug logic behind it. For debug data ready, this actually has an additional meaning, and it says, data's ready and a FIFO, one of the inbound FIFOs that's ready to be received. And that follows a pending read notification contract that I3C defines that says, now I'm expecting you to go read that data. So this basically allows the target to inform the controller, the person in charge or the entity in charge of the I3C bus, not only is an interrupt ready, and not only did I send you information on what it is, but now you have to go read something from me. This is something that's configurable with the debug opcode and debug opcode CCC with config, so that when necessary, you can go configure this and have it go read. So let's walk through these real quick here. We've kind of got these mapped into I3C bus protocol here. You've got the receipt of the target address for the IBI. You've got the debug status cause and then additional bytes that come with it, like which network adapter index and subcause. For debug error, you've got the different mandatory data byte here with the error code and additional data bytes here that show what happened, what went wrong. For the debug data ready cause, this actually is a pending read notification, and this is something that's defined in I3C version 1.1 as there's a contract associated with it. Once I've notified you of this, you, the controller, are obligated to come back and read this data. And the recommendation, of course, is that the I3C controller immediately turns around and goes back and reads from that same target, pulls those data bytes, and consumes that data and does what it needs to do with it. So, again, this is something that really this feature really shines when you have an I3C controller, such as an I3C HCI compliant controller that can do this. It doesn't have to be that way, although any I3C bus controller can do that, as long as it's able to go follow the terms of the pending read notification contract. The other interesting thing to know about debug data ready is that it automatically switches you to that particular network adapter that has debug data that's ready to be read. So you don't have to go back and do debug opcode, select that network adapter, choose the one that had data ready to go. It's automatically selected for you. So enabling an ecosystem for debug for I3C is going to take a couple interesting components to make work. Implementers are going to need to go extend I3C target logic to support these new debug CCCs, handle these new types of IBIs, and also connect up to various types of debug logic and handle the network adapters and implement the state machines and go deal with the FIFOs that deal with private writes and private reads and that logic there. So that's going to need to be something that implementers need to be aware of. And I think the standard behavior in a debug for I3C spec defines the normative behavior, defines some options that implementers can choose for what they need to do, like for which types of network adapters, what are your FIFO sizes, those sorts of things. So you have that flexibility. The I3C controller interface, there are a couple standards. We'll suggest a couple here. I3C HCI, of course, I mentioned earlier. Another interesting thing is, MIPI is actually helping to define through the USB-IF a standard device class for USB to I3C. So this is something that we're helping. We're actually looking for additional partners to help us out with this. For those who are interested, please seek out your USB-IF standards development people. Find that out. One of the other things is that we're trying to define standard debug connectors that include I3C pins. Now, MIPI does have standard specifications, such as the narrow interface for debug and test, that have pins that could be used for I3C as a narrow interface. We're working on defining a standard one that explicitly calls out, this is for serial data, this is for serial clock. We're looking for thoughts on what side of connectors would actually be useful to extend for that. So, those who are able to contribute on that, please send us your feedback. We're interested. So to kind of wrap things up here, we've got some framework here for a debug interface that's scalable, that can be controlled here from multiple places, multiple points of entry, or multi-mastering as we call it. It handles power management. It is scalable. It's got a lot of these things that address, things that the legacy interfaces just don't handle very well. Or don't handle at all. We build on the strengths of I3C. We build on these core capabilities. It's at its core, we really only need the two wires. We can have hot joins. We can handle IBIs. We have broadcast messaging. We use these mechanisms to our advantage to build a debug interface that's robust, that's scalable, and that standardizes the data exchange mechanisms so that implementers really don't have to worry about defining a whole lot of new things for this. They can take advantage of this framework here and build something else with the standard mechanism. And I think that's what's going to make debug for I3C hopefully successful in the ecosystem, is getting a good base specification, providing the right level of options, and letting implementers do what they need to within and through that mechanism. So with that, I've got some links for more information here. Hopefully we'll have a way to make these available. We've got MIPI Alliance's website, of course. We've got the various specifications that are available for debug, including debug for I3C. We've got an architecture overview for MIPI debug specifications and how these all fit together. Of course, we've got I3C, the specification itself, and then debug for I3C on its own here. So with that, I'd like to open it up for questions and hopefully answer them as best we can.